Hi everyone! In the last few lessons, you geared up for the binomial theorem by investigating the patterns that sequences can create. Now it's time to investigate another mystery inherent in the binomial theorem. What in the world is that weird symbol? If you haven't completed the warm-up activity yet, pause the video and complete that now. Oh, come on, just adding 5 terms together? That's like nothing. This is pre-calculus. We can do way harder things than that. I mean, at least have us add 10. No, 30. No, 100 terms together. Yeah, good point, Mia. Just generating 100 terms would take forever, and then we'd have to take the time to add every term together. We're busy people. We don't have that kind of time, even if we used a calculator. But in pre-calculus, we're all problem solvers, so let's find a way to solve this problem efficiently. First things first, how can we write a sum with 100 terms without actually having to write all 100 terms? Oh, I know! Let's use summation notation. Summation notation is a way of indicating the sum of multiple terms in a sequence without having to actually write out the entire list of numbers. You'll know summation notation by this symbol, sigma. It's like putting a big S there for sum, except the Greek version, because mathematicians love their Greek letters. Sigma will be followed by the explicit formula for some sequence. That way, you know what sequence is being used to generate the terms being added together. But it's not enough to just say the sum of terms in this sequence, because sequences just keep going forever. To complete our summation notation, we need a few more pieces of information. A variable below the sigma symbol, the index of summation, tells you which variable to substitute for, because some sequences have more than one variable. The index of summation will be set equal to a number known as the lower limit, which indicates the first term in the sequence to be added, because a sum doesn't always start with the first term in its sequence. The upper limit above the sigma symbol indicates the last term in the sequence to be added, so that we know when to stop adding terms. With all of these pieces in place, we have all the information we need to sum up terms from any sequence. Here's a sum written in summation notation. It reads, the sum of terms in the sequence in which each term is equal to -10 plus 6 times 1 less than the term number for values of n from 2 to 5. Now that we can read summation notation, let's see what's actually going on with it. Let's take this summation notation and expand it to see what's actually happening behind the scenes. The lower limit is 2, and the upper limit is 5, so we need to add together the second, third, fourth, and fifth terms in the sequence. Since the index of summation is n, for each term we take the explicit formula and substitute the term number for n. 2 minus 1 is 1, 6 times 1 is 6, and -10 plus 6 is -4. The first term in this sum, a sub 2, is -4. Pause now and try to finish this sum on your own. When n is 3, we get 2. When n is 4, we get 8. And when n is 5, we get 14. How did we know to stop when n equals 5? Why wouldn't we keep going? Because the upper limit tells us to stop when the index of summation is 5. If we add all of the generated terms together, we get a total of 20. And we're done! The sum of terms 2 through 5 in this sequence is 20. Now it's your turn. Pause the video now and try out these 3 examples in your guided notes. Then come back when you're finished. How'd you do? Let's check our answers. For this sum, we needed terms 1, 2, and 3 in the given sequence. That gives us 7 plus 9 plus 11 for a total sum of 27. For number 2, note that the lower limit is not 1. This sum will start with the 4th term and end with the 9th term. Here are each of those terms. Check them and make sure your work matches up. The sum of these terms is negative 120. Number 3 was a little different because it uses a geometric sequence, but you're already a master at those, so no biggie. 1 plus 3 plus 9 plus 27 comes out to a grand total of 40. But what if we want to go the other way? What if we have a sum of terms in a sequence taking up a bunch of room, and we want to condense it into as small a space as possible by writing it in summation notation? First, let's analyze the sequence to determine its explicit formula. Take a moment to do that now. The initial term is 1.5. Since the terms double each time, this is a geometric sequence with a common ratio of 2. In geometric sequences, there's only one variable, so that variable is the index of summation. What would our lower limit be? In other words, what term is first in this sum? We actually already answered that earlier when we identified the initial term for the explicit formula. Whenever you condense a sum into summation notation, assume the first term in the sum is also the first term in the sequence, a sub 1. That way, the lower limit will always be 1. And how do we know the upper limit? Well, our sequence includes terms 1, 2, 3, 4, 5, and 6, so we stop at term 6. This is another benefit to assuming the first term is a sub 1. The upper limit just ends up being the number of terms that are being added. And just like that, this sum has been condensed into summation notation, and we learned some quick tricks to do it. Now you try. Pause the video now and try writing these sums in summation notation. Then unpause when you're ready to check your answers. Let's see how you did. For number 1, the initial term is 2, and if we analyze the pattern in the terms, we notice that they're doubling in value, making this a geometric sequence. We already assumed that 2 is term number 1, and we're adding 5 terms together, so the upper limit is 5. For number 2, let's just go ahead and stick that automatic n equals 1 below sigma. We have 6 terms here, so the upper limit is 6. The sequence starts at 7, and each term is 3 more than the previous. And there we go. Our summation notation is done. Oh wow, number 3 has a long sum. Wait a sec. Is this a sum if there's subtraction in it? Oh, right! Subtraction is the same as adding a negative number. Whew, this had me worried for a second. This sum has 9 terms, making the upper limit 9. The terms follow an arithmetic sequence starting with 17 and decreasing by 4 for each consecutive term. And finally, number 4. Oh, wow, that's a really long sum. Now, this is why summation notation exists. This sequence starts with 1,600. Then each consecutive term is half of the previous term for 10 terms. This is why summation notation is so helpful. Even if the sum had 1 million terms, it could still be written in this same quick, short notation. Great work! Let's review our key takeaways from this lesson. Today you learned the components of summation notation so you could read and interpret it. You learned how to take summation notation and expand it into a sum of terms. And you learned how to go the opposite way too, taking a long sum of terms and condensing it into summation notation. Now that you've finished the lesson video, it's time to practice what you've learned with the additional practice in your guided notes. Once you've completed that and checked your answers, you'll be ready for the online practice. Then, when you've mastered the art of summation notation, you'll be ready for the next couple lessons, where we'll learn some tricks to quickly calculate the total of even the longest of sums. See you then!
Hey, hey.